Ever get that sinking feeling when your brand new machine learning model completely tanks? Yeah, we've all been there. You're just staring at the screen, wondering what on earth you're supposed to tweak next. Well, welcome to this explainer, where we're going to turn the dark art of machine learning debugging into a predictable, systematic engineering discipline. Today, we are taking the guesswork out of the entire process. Look, it's virtually a law of nature. The first time you implement an algorithm, it's going to fail. In fact, Stanford's Andrew Ng actually recalls this one Halloween weekend where he coded up a softmax regression on his laptop, and it worked on the very first try. He was honestly so stunned that it worked right out of the gate, he spent hours frantically hunting for a bug that literally didn't exist. I mean, it is just that rare for a model to work perfectly on day one. And because of that reality, building algorithms is fundamentally an exercise in debugging. So, here is our playbook for today. We'll start with the myth of first tries, move into diagnosing bias and variance, figure out the optimization dilemma, learn how to isolate pipeline errors, and wrap up with ablative analysis. Let's dive right in.
Part 1. The myth of first tries. Shifting from black magic to science.
Think of this upcoming framework as your medical toolkit for machine learning. When a model fails, it's so common to see developers waste weeks just randomly guessing solutions. They'll go scrape a ton of new data or blindly scramble their feature set, relying entirely on gut feeling. Our goal today is to replace those random, expensive guesses with systematic debugging. The absolute best way to start a new project is to build a quick and dirty implementation of your algorithm. Just get it running. Once it's running, you use logical diagnostics to isolate exactly what's failing, much like a software engineer systematically hunts down a bug in traditional code. Moving right along to part 2, diagnosing bias and variance. This is the ultimate performance test.
Okay, so this is arguably the single most powerful diagnostic tool you have for analyzing performance. By looking at your learning curves, you're tracking error rates as you feed the model more and more training examples. Now, if you have high bias, your algorithm is underfitting. It's just way too simple. You'll see high error even on your training set and a really small gap between training and test error. On the flip side, if you have high variance, your model is overfitting. It basically just memorized the training data. So your training error looks beautifully low, but then there's this massive gap because it completely faceplants when faced with new unseen test data.
The crucial takeaway here is that you have to match the exact cure to the specific disease. If your diagnostic points to high variance, getting more data is a fantastic idea. Or maybe you just need to strip away some features to simplify things. But if you have high bias, your model is fundamentally too simple to capture the underlying pattern. Going out and paying thousands of dollars to acquire more data won't help you at all. It's a total waste of resources. Instead, you need to add more features or throw in some polynomial terms to increase complexity. Diagnosing that learning curve tells you exactly which road to take. All right, part 3. The optimization dilemma, algorithm versus objective. What happens when your training objective looks absolutely stellar, but your real-world accuracy is, well, terrible? This dilemma is the heart of our next test. Let's say you're building a spam filter. You tune a Bayesian logistic regression model, but it's missing way too many obvious spam emails. Then a teammate steps in, tries a support vector machine, and it works beautifully. You really want to ship your logistic regression, but you have to stop and ask, is your gradient descent just totally failing to converge on the right answer? Or is your mathematical cost function just fundamentally bad to begin with? Here's exactly how you systematically answer that. First, take the cost function your logistic regression is trying to maximize and compute it using both its own parameters and the parameters found by that successful SVM. Next, compare the scores. If the SVM achieved a higher score on your cost function, your optimization simply failed. Your gradient descent just didn't find the maximum point. But if your logistic regression achieved a higher score on the cost function, and yet it still performed worse in real life, that means you are optimizing the wrong function entirely. You're getting a perfect score, but you're taking the wrong exam. And hey, this isn't just abstract theory. Take the famous Stanford autonomous helicopter project. They wanted a helicopter to fly itself. But when it started wobbling dangerously in the air, the team had to ask, is our computer simulator bad? Is the reinforcement learning algorithm failing to learn? Or is our mathematical definition of good flying, our cost function, just wrong? By using systematic diagnostics exactly like the one we just walked through, they isolated the exact bottleneck. This is vital, folks. You absolutely do not want to spend 6 years writing a PhD thesis on improving a simulator that was actually already good enough. Part 4. Isolating pipeline errors. Let's talk about breaking down complex systems. What if your algorithm isn't just one neat little equation, but a massive pipeline of chained models? Consider a face recognition security camera for a door lock. It doesn't use one giant monolithic algorithm to decide if it's you. It uses a sequence. Step 1, it removes the background. Step 2, it detects a face. Step 3, it segments the eyes and nose. Step 4, a logistic regression makes the final call. Visualizing this pipeline is absolutely crucial because a final output error could have originated anywhere along that entire chain. To stop blindly guessing where the problem lives, we use a technique called error analysis. This involves taking your development data set and, well, essentially cheating. You manually plug in perfect ground truth data. Like, imagine using Photoshop by hand to flawlessly remove a background for just one component at a time. Then you step back and see how much that manually injected perfect performance actually improves the final overall accuracy of your system.
Think about the data we might get back from a hypothetical test like this. Say, giving the system perfect face detection yielded a massive 6% boost to overall accuracy. Awesome. Perfect eye segmentation gave a solid 4% boost. Great. But giving the system a perfect 100% flawless background removal, what if that only proved the final accuracy by a tiny 0.1%?
That tells you exactly where to focus your engineering resources, the actual bottlenecks. Because if you assign 10 of your top-tier engineers to improve background removal, the absolute best you can possibly hope for is a 0.1% gain. It's a total dead end. There is a hilarious true story about a student who actually spent years writing an incredibly complex PhD thesis on dynamic background removal, literally modeling the wind blowing through the leaves of trees, all for a fraction of a percent improvement in the overall system. Error analysis is what helps you avoid stepping into that exact trap.
Finally, Part 5, Ablative Analysis, Proving Feature Value. So, while error analysis explains the gap between your current system and perfect performance, ablative analysis is the exact reverse. It explains the gap between your clever, complex system and a basic, bare-bones baseline. Instead of injecting perfection, we are systematically removing or ablating features one by one from our completed model just to observe the drop in performance. It's like a game of Jenga. This is how you prove what actually matters in your model. Say we're analyzing a high-performing spam filter. We pull features out individually to see their specific impact. Removing spelling correction causes a 1% drop in performance. Removing sender host features causes a 1.5% drop. But pulling out the text parser, that causes a massive 4% drop in accuracy. This gives us hard, quantifiable proof that the text parser is doing the heavy lifting for the model's success. Why does all this matter? Well, because if you start with a basic model at 94% accuracy, and you eventually ship a massively complex model at 99% accuracy, you have to justify that complexity. Ablative analysis allows you to confidently explain exactly how you earned those 5 extra percentage points to your stakeholders. This is essential for project reports, publishing papers, and real-world engineering where computational cost is a huge deal. If a super complex feature gives you a 0.1% boost but costs millions of dollars in server compute to run, you can confidently cut it. Let's do a quick recap. By using this diagnostic playbook, you completely transform your entire workflow. First, you evaluate bias versus variance to know right away if you need more data or more complexity. Second, you test the optimization objective to ensure you're maximizing the right math. Third, you use error analysis to find the true bottlenecks in a pipeline. And fourth, you use ablative analysis to prove which features actually provide value. You turn the absolute frustration of a failing model into a systematic binary search for the cure. Which leaves us with the ultimate question. Because as we established right at the top of the show, your machine learning algorithm is almost certainly going to fail on the very first try. So, the next time it inevitably crashes and burns, are you going to rely on black magic, gut feelings, and random guesses? Or will you step back, look at the data, and diagnose the problem like an engineer? Thank you for joining me on this explainer. I really hope this framework helps you build smarter, much more efficient models. Catch you next time.